Hello and welcome to this next lecture of course Basics of Semiconductor Devices and Technology. Now in this module I'll be talking about electrical conduction in semiconductors and in general electrical conduction in solids. The reason we are interested in understanding electrical conduction in semiconductors because eventually we want to develop or determine the current voltage characteristic of semiconductor devices that we will be dealing with at later stage, and therefore as a first measure it is important to understand or consider the electrical conduction in solids and relate it to the band theory we developed in the previous modules. So let's let's begin by considering the motion of electrons in various allowed energy bands. For that we try to understand the covalent bonding in a semiconductor. So as I discussed in the past, we talked about the electron behavior confined to a single atom. And when you bring all these atoms closer, the atoms try to or their atomic orbitals try to interfere or overlap with each other, and in the process of this overlap they form these covalent bonds. Now in the covalent bond the valence electrons are shared. In case of silicon, let's say what you see here is a very simplified picture of a one-dimensional crystal lattice. Let's call it silicon crystal lattice, though the silicon crystal lattice is slightly different. It doesn't look like this, but let's assume this is silicon atom, and these are arranged in a one-dimensional fashion. Let's say these are silicon atoms. These are all silicon atoms, and so on, and they are arranged in this particular two-dimensional fashion. I said one-dimensional if you consider one of these direction, but if you take this plane, you can consider them arranged in a two-dimensional plane or two-dimensional fashion, in this particular fashion, where each silicon atom has four valence electrons and 8 valence states. So I also discussed earlier that each silicon atom has 4n valence electrons and 4n of empty states, right? So now what will happen, each silicon atom has 8 states and each silicon atom has 4n valence electrons. So now these 4n of each silicon atom will share, so these are these 4n, and it will share with additional adjacent silicon atoms, each individual electron, forming this covalent band or covalent bond, and in this fashion the crystal lattice will be arranged, or the bond across individual silicon atoms will be formed in a crystal lattice. Now let's rub this. So now what happens at temperature equals to 0, there is no energy given to the system. The energy given to the system is 0. In this case it's the thermal energy, but when I say energy given to the system is 0, means there is no external energy, no external force or energy applied to this system. And in this case, if there is no external force or energy given to the system, all the bonds are intact and you don't see any free electron. The free electron will be present when one of the valence shell is not overlapping or not bonded with the adjacent valence shell, and therefore that electron is freely available to do or to roam around in the crystal lattice. And that's the case when the system experiences a finite temperature. When the system experiences a finite temperature, that much thermal energy is now given to the system. Now you may be thinking that how much energy is needed, and you may remember the numerical problem which we discussed, that if you have a lattice or an atom, and then let's say you have an electron bounded, we remember we discussed about this potential distribution or potential function and different energy levels across that. And we also discussed that if this is a free particle, then this energy was of the order of electron volts, and if this is a crystal lattice with finite permittivity, then this energy spacing was of the order of milli electron volts. Now if this is of the order of milli electron volts, which can be even smaller as you pack more and more atoms together because of the energy splitting and in a silicon like crystal lattice, so you can imagine that if you give a finite temperature, or if you rise the temperature below 0 Kelvin, you're actually increasing the average energy across the system. You know that 300 Kelvin translates into 25 milli electron volt. So any finite temperature increase would be of the order of few hundred micro electron volts to few milli electron volts, and that's good enough energy for this covalent bond to break and the electron to get liberated or become free electron, which can roam around in the crystal lattice. Now in terms of the band theory, what is the meaning of this free electron? So we discussed two different bands. We discussed the conduction band and we discussed the valence band. This you remember from the previous lectures. Now the valence band is the band which basically holds these electrons. The valence band is the band where the electrons are or electrons have occupied those valence states, the valence shells. In case of silicon, the last time I told you that there are 4n electrons or states which are available, states which are free for each atom, and 4n states are occupied for each silicon atom. Now these 4n states which are occupied, these are also consisting of these 4n electrons. So what does this mean? That these 4n occupied states corresponds to the valence shell or the valence band, and these 4n free states corresponds to the conduction band. And any electron which basically moves from these occupied states to these free states, they actually move from this valence shell or valence band to the conduction band. Now when they move from the valence band to the conduction band, they are going to leave a positive charge across the crystal or across the atom, or inside the valence band. You can think in this way, that they leave a positive charge inside the valence band. Okay. Now this free electron, as you see, as it leaves any of these bonds, a covalent bond will break. This place you see a positive charge, and this electron leaves out inside the crystal lattice, and this free electron can move freely in whatever direction it wants to move under the random thermal drift, or if you apply a net force, then it will move in the direction of the applied force or in the influence of the applied force, which can be an external electric field or some other force. Now if the electron is moving randomly, then the net drift velocity will be 0. If it is moving in the direction under the influence of a net applied force, then it may have a finite drift velocity that we will discuss in the next slide. But let's try to understand what this whole thing means in terms of the band structure. So you remember we talked about the parabolic band last time, and what it means from the band structure point of view is that let's say your valence band, the valence band has finite number of states. At t equals to 0, all those states are fully occupied, Now what are these finite number of states? Let's say you have m number of atoms and each atom corresponds to 4n states. Then your total number of states are m times 4n roughly. So these m times 4n states are present in the valence band, and all these states, as you see represented by these dots, all these states are occupied by these electrons. Similarly, all those states in the conduction band are empty, are free, and they do not have any electron present in them. Now the moment temperature increases, the moment you increase the temperature above 0 Kelvin, some of these electrons which were there in these states in the valence band will move to the conduction band. So the conduction band will also get finite charge or finite electrons which are freely available to move in the direction applied to the force, or they are freely available to gain a certain momentum if there is an electric field or an external force applied. Okay, so now from the band structure from the band theory, can we define a material being insulator or semiconductor or a metal, right? A material which is insulator means it should have insulating properties. It should have properties such as it doesn't behave as a conductor under any condition, which means it should not have free electrons. If something has no free electron, which means the binding energy of those covalent bonds must be much higher, that at room temperature there must not be any free electron present, which means in terms of the band structure, even at the room temperature, even at T greater than 0 or close to room temperature, all the valence states must be fully occupied and all the conduction states must be completely empty. There must be no electron transition from the valence band to the conduction band, no matter how much force or how much external field or energy has been given to the system through thermal means or any other mean. Whereas if it is a semiconductor, then as you increase the temperature, a finite number of valence electrons will move to the conduction band and therefore will become or will make the material conducting. So a semiconductor in principle is an insulator. A semiconductor is actually an insulator at T equals to 0 when no external field is applied. Right? Because there are no valence electrons. But at finite temperature, some of these valence electrons will move to the conduction band, and those electrons in the conduction band will be available for conduction, will contribute to conduction, and the semiconductor will become a conductor with a finite resistivity. And that's why the semiconductor is called semiconductor, because it's both conductor as an insulator at temperatures below the temperature required for the electron to move to the conduction band, the material will behave as an insulator, and at temperatures above the temperature required for moving these valence electrons to the conduction band, the material will behave as a conductor, right? So again you can see this representation where the conduction band is always empty and the conduction valence band is always full. I'll talk about this later, that there are a lot of these electrons present in the valence band, so why they don't contribute into conduction. That we'll understand from the concept of holes, but for the time being, let's see in case of semiconductor, there are some of these valence states unoccupied, so there are free states available in the valence band. These are actually called holes, and I'll introduce concept of holes a little later. And all these electrons which move from the valence band to the conduction band, they become free electrons in the conduction band, and all these electrons are now available for moving freely across the crystal lattice, and they contribute in the conduction. Apparently the holes also contribute in the conduction. I'll talk about that a little later. Now if it is metal, the difference in the metal is following. You actually have two type of metals. Either the metals, the the conduction band, even at t equals to 0, your conduction band would be partially filled. If the conduction band is partially filled even at t equals to 0, these are defined as metals or materials having metallic properties. Or you may have materials where there is an overlap of the conduction band and the valence band, and therefore there is no transition energy involved for electrons to move from the valence state to the conduction state, and as a result of that you have enough states available in the conduction band, and all these electrons are available to freely move through these conduction states. So these materials are also known as metals. Okay, now having introduced the concept of electrons and having discussed the possibility of movement, it's imperative that we talk about the current or the drift current. In this case, the current which is produced by the drift of carriers is called the drift current. Drift means you apply an external field, you apply an external force, you give an external force to the charged particle, and as a result of that the particle drifts in the direction of the force and that current and result into a current, and that current is called the drift current, right? So let's say you have a volume and the current flows in this direction, right? And let's say this volume has n number of positively charged ions, and across each charge ion or across each ion the charge is q, and let's say if they are moving with velocity vd, where we call drift velocity vd as the drift velocity, through a cross section which is this, and I call this cross section as, let's say, some centimeter square. Let's say this is 1 centimeter square, right? So now the total absolute current density through this cross section is going to be total charge times velocity. Total charge here is q times n and velocity is vd. So the J, which is the current density in ampere per centimeter square, is going to be q n vd, where vd is the drift velocity. Later on I will show you that this vd translates into another parameter which is mobility times electric field, mu e, but that's for later in the lecture. For the time being, you see that current density equals to charge times the velocity. Now what does it mean in case of external force applied? So there are two ways. The vd, for instance, let's say vd could also be just a thermal velocity. If it is thermal velocity, then the net thermal velocity would be 0 and therefore the net current would be 0. The reason is that you can write this equation, you can write this also in this form, where you say that it's the summation of q for all those particles which are moving with drift velocity vi, and you sum it for all those particles. Now some of those particles may move into some direction, let's call it vi plus, and some particles may move in the other direction, let's call it vi minus. So the net sum, if this is random thermal motion, is going to be 0, and therefore the net current density is going to be 0 across a given cross section, because the amount of current which comes out of this plane, pretty much the same amount of current will go inside or will cross through this plane to the other side, and therefore the net current under the random thermal motion is going to be 0. Now let's assume that we are talking beyond random thermal motion. We have applied a certain field. Let's say you have now a force applied in this particular direction. So if you have a force applied, the force could also be in form of a certain electric field. If you have an electric field applied, then the carriers are going to be drifted in the direction of the electric field, and in the opposite direction of the electric field depending on the charge of the carrier, charge of the particle, right? So if the net drift velocity becomes finite, the net momentum of the electrons will also be finite. If the net momentum of the electrons are finite, then your band will look something like this, where most of the electrons have occupied a certain finite momentum, right? And that momentum is defined by the force or the direction of force. So you can think in this way in terms of the band structure. Around the k equals to 0 point, a certain energy states are going to be occupied depending on the allowed energy states and depending on the momentum of the particle. Now if this was just the random thermal motion, then you can imagine that this will look like this, where you have equal number of electrons for the negative momentum and the same number of electrons for the positive momentum. So the net momentum becomes 0, and as the net momentum becomes 0, the net velocity becomes 0 and the net current therefore becomes 0. But in this case you have a net finite momentum. Net finite momentum means or there is an imbalance of momentum between positive and negative, and therefore you have a net finite momentum. Net finite momentum means a certain number of energy states at one side of the band or one side of the band are going to be occupied, whereas the other side of the band will be less occupied compared to the other side. Okay, so now if we have understood the concept of velocity, the concept of drift velocity, and we briefly touched based on the force, then let's also try to extract the effective mass. You know that the force is nothing but the mass into acceleration. This is force, right? But would this mass or the electron mass inside the crystal lattice would be same as the electron mass in free space? No, and we'll see how. So you can imagine that, let's assume that the total force on exerted on the electron would be a force which is external force and a force which is internal force. The external force would be the applied electric field or the external temperature and so on. The internal force could be, let's say, the Coulombic attraction because of the nucleus, the Coulombic attraction because of the neighboring electrons, or the Coulombic attraction or the repulsion because of the positive charge which is left at the crystal lattice site. So because of these repulsive and the attractive forces internally present in the crystal, you have a net internal force. Now it's very difficult to calculate that net internal force, whereas we know what could be the external force because we apply that. So what we do, we assume this to be a single entity, or you can think in this way that you can write this F external equals to MA minus F internal, and F internal is also of the order of some mass. Let's say this is mass hash versus acceleration. Acceleration is common because we are talking about the same particle. So you can write this effectively, taking into the account of this F internal, you can write this effectively as F external equals to M star A. Now this M star is the effective mass of the particle inside the crystal lattice, and this M star accounts for all the internal forces applied on the particle which may change its dynamics, change its behavior, or change its acceleration. So rather worrying about different accelerating factors, I would say different accelerating factors, this external acceleration, because of the if it is free particle it would be something else, if it is inside the crystal lattice it would be something else. So by you can account for a common acceleration factor, and that by taking an effective mass of the particle when the particle is inside the crystal lattice. Now you can also think of this in the following way, that let's say you take two beakers, right? One is full of water and other is full of some oil. Of course the oil is going to be a lot more viscous than water. Now if you put a metal object from the top and drop it, it will go down under the influence of gravitational force, but there is also an internal force exerted on this body, on this ball, which is because of the liquid or the fluid which is inside the beaker. So in the case of the first beaker it is the water, in the case of second beaker it is oil. Of course oil is a lot more viscous, so you know that in this case, in the second case, the metal object will take a longer time to come down versus the metal object takes the time in the first case, in case of water. So here T1 is less than equals to T2. This also means that if this has a velocity v1 and this has a velocity v2, v1 is greater than v2. Or if this has an acceleration a1 and this has an acceleration a2, a1 is greater than a2. Now you can imagine that both had the same mass outside the beaker, both had the mass m, but the moment they go inside they got a different acceleration factor because of the internal force being different on them. So rather worrying about the internal force, now we can modify this mass, we can call it an effective mass, and this effective mass will be function of the system which we are dealing with. If it is beaker number 1, the effective mass will be smaller. If it is higher, if the beaker number 2, the effective mass will be different compared to the beaker number 1. So rather worrying about the acceleration being different, rather worrying about the internal force inside these two systems, we basically take another parameter, we modify the mass as an effective mass, which will account for the change in the behavior or change in the dynamics as the particle moves inside a given system. If it is silicon, the effective mass will be different, because for the same electron the effective mass will be different compared to if it is gallium nitride, gallium arsenide, silicon, silicon germanium, and so on. The reason is that their crystal lattice are all different, the kind of covalent bonds they will form will be different, the kind of internal forces therefore they will exert on the free electron will be different, and the number of free electrons at a given temperature will also be different. So therefore the amount of force exerted in the free electron inside the crystal lattice will also be different. Therefore the same electron in free space having a well-defined mass will have a very different mass the moment that particle is placed inside a crystal lattice, and that mass will vary or will depend on the crystal lattice we are dealing with. Okay, so since I discussed the effective mass, or I gave you a feel for what the effective mass would be, let's see if we can derive a relation for effective mass and make a correlation with the band structure or the EK diagrams. So to derive a relation, let's start with the EK diagram of a free electron or electron in free space. You know that it's a parabolic relation, which is energy equals to momentum square divided by 2m. We can translate that into K relation as well. You remember that the momentum we earlier defined as h bar k, so we can write momentum as h bar k, and it becomes h bar square k square divided by 2m. Now from here let's take the first derivative of the energy, so dE by dk, that becomes this will become 2 h bar square k by 2m. This cancels out, so it becomes h bar square k by m. You can rearrange it, and d by dk becomes h bar p divided by m. Now if I move the h bar to the other side, 1 upon h bar d by dk, so this becomes p by m, and p by m you know is nothing but mass into velocity. Momentum is mass into velocity divided by m. Mass cancels, we get velocity. So 1 by h bar d by dk is equals to velocity or the carrier velocity. So the slope of the band structure tells us the carrier velocity. If I explain this further, if the slope is steeper, which means that the particle in that particular band will have a higher carrier velocity under the influence of a given field versus the other band. Or let's say if I show you 3 different scenarios, let's say this is scenario number 1, 2, 3, and therefore this is V1, this is V2, and this is V3. Here V3 is greater than V2 is greater than V1. Okay, now let's see what else we can extract out of this, right? So again we go back to this relation from where we started, this relation or this relation. So here if I rewrite this again, d by dk is equals to h bar square k by m. Now if I differentiate this again with k, what do I get? If I differentiate this again with k, so I take the double differentiative of the energy, what I get is h bar square by m. If I rearrange this, I get 1 upon h bar d2 by k equals to 1 by m. If I further rearrange this, the inverse of the mass is the double differentiative of the energy band, right? Let's clean this up. Okay, so what does this mean? This means that again if we go back to the same band example which I took, if I say that this is M1, this is M2 and this is M3, we are talking about the inverse of the double differentiative or the inverse of the slope, which means that in this case here M3 is the lightest and M1 is the heaviest. In terms of mass, this will follow M1 greater than M2 greater than M3. Now the same we can basically use for the band structure that we are aware of for semiconductors. It follows a parabolic approximation. At least for the lower values of k, the parabolic assumption is valid. So you can calculate the mass, but even at the higher values of k, if you take the slope, if you find the slope, you get the velocity, and if you take the double differentiative, you get the mass. Let's analyze this band structure. For instance, let's say if this is silicon band structure, what it tells is that it follows a parabolic approximation near k equals to 0. Both for the valence band and the conduction band, it follows a parabolic approximation. But as it moves further, for higher and higher values of k, or higher and higher values of k, let's say greater than 0, the parabolic approximation is no more valid and it becomes linear, and gradually it saturates at the point which is the Brillouin boundary, right? So it starts saturating. What does this mean? It means that as the particle gains higher and higher momentum, the velocity of the particle falls and the carrier gains more and more mass as it moves towards higher and higher momentum. Or as the particle gain more and more energy, the particle's velocity will drop uh, and particle's mass will increase. The particle will experience a higher repulsive force that its effective mass will increase, and since it's experiencing a higher repulsive force, the velocity will drop. The same is valid for holes, or the same is valid for the valence band. Valence band will have the holes. Again, for the holes, as the holes gain more and more momentum, the velocity of the holes will fall, and the effective mass of the holes will increase, because the particle will experience higher repulsive forces as it gains more and more energy or the momentum. Now you can also think in this way that gaining higher energy or the momentum means it's basically in the beginning the electron may still be confined to a region around the crystal lattice or the atom from which the electron has liberated. Though the electron may not have moved, but still it may be somewhere around the atom. As it has gained momentum, it means it's basically accelerating towards the other atoms, accelerating towards regions from where it may experience rather repulsive force, or experience, let's say if there is another crystal atom, or the atom of that crystal, it will experience some kind of a repulsive force. It will experience some kind of a scattering from that atom. It may experience some kind of a scattering from that atom, and therefore the electron may drift into some other direction under the influence of that particular repulsive force. So this repulsive force can be seen as, or this repulsive force will be experienced more when the electron has gained higher energy or higher momentum, which means it's kind of approaching towards the other crystal atoms, and that's when its velocity will try to slow down, or in other words, it will experience a rather higher effective mass, right? Now you can also write the acceleration or the effective mass in form of the field and the charge. You know that the force across system or force across a particle is also negative of charge times electric field. Now this force can be written as mass into acceleration. So the acceleration therefore can be written in this form, which is inverse of the effective mass and directly proportional to charge times electric field. We'll talk about this in a rather greater detail a little later when we talk about the velocity. Now you can also get a feel for the effective mass for electrons and holes inside silicon. So for electrons inside silicon, the effective mass in a certain plane is on a higher side. So the effective mass of free particle, let's say, is m naught. The same effective mass for the electron inside the crystal lattice is greater than m naught, which is 1.08 times m naught. Now for holes, it's the other way around. So in case of holes, the effective mass is lower than the effective mass of the mass of the electron in free space. Okay, so now I talked about holes. I think electrons we fairly understand now, and I talked about holes. So it's important for me to explain what these holes are. You remember when I said that at a finite temperature the covalent bond will break and an electron will become free and it will be liberated or it will be available for random motion as a free electron somewhere inside the crystal lattice. Right? Now, as a function of this bond breakage or bond breaking process or the breaking of the covalent bond, we actually leave a positive charge at the atom site. Now, this positive charge is also an unoccupied state, or a bond which was broken. Now this bond got broken because of a finite temperature across the system. The same bond has a finite probability of again, or the same state has a finite probability of again occupying an electron. In other words, the same bond has a probability of again bonding with the adjacent atom if it can occupy electron from some other state or from some other bonded state, and that's what happens. So if you see in this case, it is shown that the system will also allow breakage of other bonds, and it will liberate an electron, and that electron will go and passivate some broken bond and will form a covalent bond over there. You can also think in this way that let's say a bond which was earlier broken here, and the electron moves from this point, goes here, it forms a bond and creates a positive site here. So you can think in this way that rather an electron moving from this side to this vacant side, a positive charge actually moved from the vacant site to the previously filled site. So here the movement of electron in the opposite direction, the movement of electron from one occupied state to another free state, can also be seen as movement of these positive charges from free state to an occupied state. Now these movement of positive charges is basically denoted as holes or positive charges. So in the previous, in both the cases, it's basically these are electrons which are moving, but in the other case the electron was under a drift movement. So electron moved in these empty spaces of the crystal lattice, of course under the influence of internal and external forces. But when it comes to holes, these are electrons which are moving from these occupied states to a free state, which can also be seen as a hole or a positive charge moving from free state to an occupied state. And this positive charge motion or the opposite electron motion through these available states is called the movement of holes, and these positive charges which are moving from one free state to the other unoccupied state are called holes. Now the question is when this movement will happen and why it doesn't happen at t equals to 0. At t equals to 0, all the valence states are completely occupied. So when all the valence states are completely occupied, there is no way these holes can move to another state, or because these are the movement of electrons from one state, one occupied state to another free state. If there are no free states at t equals to 0, no electron can move to another state because there are no free states, and therefore there is no hole movement and no hole current. Similarly, there was no free electron in the conduction band, so there was no electron current. Now in case of the case when the temperature is finite, you have a certain number of free states available, and you can think of these free states as these positive charges. So you can think of these positive charges moving inside the valence band in the similar fashion as the electrons moved in the conduction band, and therefore they also get influenced by the external electric field. They also see an acceleration, but the difference here is that the charge is considered as positive, and they will have a different kind of net effective mass because they are influenced by a different kind of force, and their motion is defined in a very different fashion. In case of electron, the motion was rather through these free spaces inside the crystal lattice. In case of holes, the motion is through these bound states inside the crystal lattice. So of course the nature of the force experienced by these holes would be different. The way these holes move in this hop off fashion is also different, and therefore the net effective mass of these holes would also be different than the net effective mass of the electrons in the same crystal lattice. Okay, so now given that we have understood the concept of electrons, holes and their movement fairly well inside the crystal lattice, it's important to now think or now consider the bigger picture. The bigger picture means that now you have a system with hundreds and thousands and millions of atoms. So you cannot basically picturize the dynamics of every single electron. You cannot basically visualize the dynamics of every single electron. You cannot calculate and consider the dynamics of every single electron, every individual electron. So here we again apply statistical mechanics and quantum mechanics, and we try to get a statistical picture of the dynamics of electron. Now, to get the statistical picture of the electrons, we have to understand couple of things. What are these couple of things? One is that what are these states, how these states are distributed across the crystal lattice. We know that if it is a single atom, we have a recent understanding of these states. We understood that those states were quantized in nature, and depending on the system that we dealt with, whether it was particle inside a infinite potential well or it was particle confined to a crystal lattice, we calculated those discrete energy states. So you know that for a given energy level or from a given energy level, what kind of or in a given energy range, what kind of states or number of states which were available when the particle was confined, when we dealt with a single particle and the particle was confined to a given space or given volume. Now here we are dealing with millions and billions of particles confined in a larger volume, which consists of many those atoms, and these particles are going to be confined to those atoms, and therefore we have to now understand the dynamics of or the distribution of these particles, the distribution of these states in a more statistical fashion, right? So that's where we introduce the term density of states. I will skip the mathematical derivation for it, but what I'm trying to explain you is that the density of a state means that in a given volume, let's say you have a crystal lattice. Let's say this is a given volume in the order of centimeter cube. Now in this given volume, how many total number of states are present? The total quantum states, and how these quantum states are distributed across energy levels, right? So in the older case, you remember when we dealt with, let's say, a particle in a finite or infinite potential well, we remember we calculated these discrete states all the way from E1 to En, and we knew that in a given volume you actually get infinite states. It can go all the way, if the potential barrier is infinite, you can go up to all the way up to infinite values, right? Although they are discretely spaced. But you can also define another parameter which says that in a given energy window, let's say from 0 to 1 electron volt, or let's say from 1 to 2 electron volt and 2 to 3 electron volt, how many energy states are present. Let's say here you have 1. Let's say from 1 to 2 electron volt you have 2. Let's say from 2 to 3 you have 3. Let's say 3 to 4 you have 4. So it will look like this, that if I plot energy 1, 2, 3, 4, what I get here, I get 1, at 2 I get 2, 3, 4. So it gives me some kind of a linear energy versus density of a state relation. Similarly, in the crystal lattice, it would be something else. And that would be defined based on how individual states are distributed in the energy space. In the energy space means, let's say in a three-dimensional volume, in a real space, you can think in this way that let's say you have a building, and in that building at the ground floor you can occupy, let's say, only one person. At the first floor you can occupy two people. At the second floor you can occupy maybe, let's say, four people, and let's say going forward at the nth level you may occupy some n to the power m function. So you get a function which basically tells how you can occupy, or how many states are available at each floor, at each level. Similarly, for solids you can get that kind of energy or that kind of density state function which tells that at a given energy level how many states are occupied, or in a given band of energy level how many states are available, or how many states are present and how many states can be occupied, right? So in case of solid, that is given, or the density of state is proportional to the square root of the energy times a constant. The constant is 4 pi times 2 times mass of the electron to the power 3 by 2 divided by h to the power 3. Now if it is a semiconductor, then it's going to be slightly modified in this form, where the density of state, the mass will become effective mass. If it is conduction band, then it becomes effective mass of the electron. If it is valence band, then it becomes effective mass of the hole, and the energy will get shifted by the conduction in the valence band. So if it is conduction band, the energy becomes E minus EC, because at E minus EC equals to 0, the density of state must be 0, and as you go in the conduction band, the density of states will become finite. As E becomes lower than EC, which is this forbidden gap, you must not have any density or any states present. Similarly, which is if it is valence band, the relation is modified by EV minus E, which means that you have finite density when EV is greater than E. EV is here, which means when we go down in the energy, you get a finite density of states. Now if you plot this, it looks like it's a function of like this, which means as you increase, as you go up in the energy level, you actually get more and more states available. You get more and more states available as you go up in the energy level. It's a very similar case as I was explaining as the layman example, that as you go to the higher levels in the building, you have more and more rooms available for people to occupy. Similarly, in the crystal lattice, as you go to higher energy levels, you get more and more states being present to be occupied. You can also think of this in case of a particle bound across a crystal lattice. You remember we solved Schrodinger equation for hydrogen atom, and therefore we calculated all the quantum numbers and quantum states, and you remember as the quantum number n progresses from n to 1 to 2 and 3 and 4, the number of states, the quantum states available started increasing. So for n equals to 1, you could occupy 2 states. For n equals to 2, you could occupy more than 2 states. N equals to 3, you can get even higher than the previous number of states, and so on and so forth. So as you progressed to higher and higher energy levels, the energy was progressing with n, only n. So as you progressed with higher and higher energy levels, you get higher and higher states available to be occupied. In the same way, for solids, as you progress higher and higher in the energy level, you have more and more states available to be occupied. And this distribution of states as a function of energy is called density of states. Now this was about the density of a state, which means that the number of rooms available at each floor, if I put that in the layman term. But then question is, how are these states occupied? Are these states occupied randomly, or is there another function which can define that how these states are occupied statistically? Of course, you remember that we must always follow the Pauli exclusion principle, that no two electrons can occupy the same state, which means that if an state is occupied, that state cannot be occupied by another electron. So that's something that you always need to remember. But then other aspect is that let's say if there are so many rooms available, all the way from the ground level to whatever level that you want to occupy, then what probability or what statistics is followed to occupy all those states or higher energy states? Is there a function, is there a probability function which can explain that filling of the states? So the function which explains that is called the Fermi-Dirac probability function. The Fermi-Dirac probability function, which is 1 over 1 plus exponential E minus EF divided by KT, where EF is a Fermi energy level, a Fermi energy. I'll explain that a little later. E is the energy that we were talking about, which is progressing from 0 to some higher number. T is the temperature, K is the Boltzmann constant. So the Fermi-Dirac probability function, or the distribution function, gives us the probability that a quantum state at energy E will be occupied by an electron. Now this is also derived by the number of particles per unit volume available and the number of quantum states per unit volume per unit energy. And we'll use that later to calculate also the total number of electrons available per unit volume per unit energy, but that's for next lecture. For the time being, let's see that what's the meaning of this Fermi-Dirac probability function, or the probability distribution function, explaining the number of electrons, or the quantum states at energy E being occupied by an electron. So you can also, let's say, if I give you a layman example, let's say you have a tank which is full of water, and the water is at finite temperature, or let's say it's boiling. If it's boiling, then some water droplets would be above the reference level and some water droplets would be below the reference level. You can think of that as, let's say, there is a reference level which would be the level when the water is at a freezing point, or the water is still, water is not moving, and if the water is boiling, some water droplets will be above the reference level and some water droplets or some water will be below the reference level. Now that reference level is basically the Fermi function at which will always be reference level no matter what the temperature is, assuming that the water is not expanding as a function of temperature. And the water going above the reference level signifies that some states above the reference level is also occupied at that particular temperature. In this case, you can imagine that we talked about those different floors and those different rooms. So these rooms were the number of states being available at different levels. Let's say this was E1 and this was En. Now you may have some of these states occupied and some of the states being emptied. So the function, the distribution which explains or the function which tells you the distribution of filling of these states as a function of energy is the probability distribution function. Now if I plot this, the probability distribution function will look like this, that it will start smearing out at the energy level which is EF. Now EF at t equals to 0, EF is the energy level where the probability of filling the state is 1 by 2. How? If we put EF equals to 0 here, it becomes 1 upon 1 plus exponential 0 by kT, which is 0. So it becomes 1 upon 1 plus 1, which is 1 by 2. So EF is the energy level which is at which the probability of filling the state or occupying in a state is 1 by 2, which means that no matter what the temperature is, the number of states below the EF level versus number of states above the EF level, the probability at EF will always be 1 by 2. However, when t equals to 0, EF can also be seen in this way, that if t equals to 0, if we put t equals to 0 here, this function will become minus or plus infinity depending on the value of E and EF. So if E minus EF is greater than 0, then this becomes exponential of infinity, which means the whole function becomes 0. And if E is less than EF, this becomes exponential of minus infinity, which means the whole function becomes 0, and therefore this becomes 1, which means when t equals to 0, the probability of finding the states occupied at energy is less than EF will be 1, and energy is more than EF will be 0. But when it's a finite temperature then the function, though the probability of filling the state at EF will be 1 by 2, but above and below EF the function would smear out as it is shown in this case, which means the probability of filling the state at E greater than EF will be same as the probability of a state being unoccupied will be same. The probability of filling the state at energy greater than EF will be same as probability of an state being unoccupied at energy less than EF. So this is what the Fermi Dirac distribution function is in a nutshell. We can try to understand the relevance of Fermi energy in a bit elaborate fashion, in a layman fashion. As I already gave you the water tank example, you can think of EF as the reference level which is at the freezing point, and assuming that the water is not expanding as a function of temperature, and if the water is boiling, then you have some states being occupied above because of these waters juggling above the reference level, and of course some states below the reference level will be empty. So this condition is in the thermal equilibrium, where you have some states above the reference level being occupied, and some states below the reference level will be empty. Now the other understanding of the Fermi level is following, that in a given system the Fermi level will always be the same. What does it mean? If I give you a layman example, let's say you have two systems, one system here and other system here, and they are not correlated, they are distant apart, they are far apart. So they may have different levels through which the states are occupied, and therefore different level of different Fermi levels. But the moment you connect both of them, if there is an empty state available here, these empty states will be occupied by these these occupied states, so then as a result of that, these empty states will also get occupied. It can be seen as so as a result, in thermal equilibrium, both the side will have the same number of occupied states, or same level till which the states are occupied, and therefore the Fermi level will be fixed or constant when you have connected these two systems. You can also think in this way, that let's say you have two water tanks, they may have different level of water, and that is all fine, but the moment you connect them, the moment you connect them with a common pipe and you allow the water to move freely both sides, then both the tanks will level equally and will come to the same water level across. So this is the Fermi energy, or this is the Fermi energy level, which explains that how the energy states are occupied above and below the reference level, and how the Fermi level is going to be aligned when you connect two systems together. Now, often in further derivations, you will come across an approximation called Maxwell-Boltzmann approximation that's used for simplifying the Fermi-Dirac distribution, because often we may be dealing with this tail, which is the region where the highest number of electrons being present. As you remember that as you progress in the energy level, the density states will increase. So this is the tail which basically talks about the region which will have most of the electrons. So we may often simplify things for easy mathematics. In computational tool, you may have option that you want to solve using Maxwell-Boltzmann approximation. That may be a faster calculation, or you want to consider full Fermi-Dirac distribution, which will be a slower calculation but will give you a rather closer calculation or closer results to what you may have measured from experiments. So that you have to keep in mind. If you simplify this the Fermi-Dirac distribution, so what we do, we basically take this up, and so it becomes another exponential function, which is a simplified form of the Fermi-Dirac function, and this will give you a good fit in a higher energy level, but it will diverge away from the Fermi-Dirac function as you go to lower and lower energy levels, as you approach closer to the Fermi level or go below Fermi level. Another thing you have to keep in mind, that if Fe is the probability of a state being occupied, 1 minus Fe is the probability of state being empty. So if I show you this, if this is Fe, then the inverse, this is 1 minus Fe, or this is same as the area here, which is the probability of a state being unoccupied, and this being the probability of state being occupied above EF. Okay, so before I close, let's look into some of the numerical problems. The first problem is that let's say the density of state for a free electron is given. I mean, this is the relation that we have seen earlier. Calculate the density of state per unit volume with energies between 0 and 1 electron volt. So this is a constant that I already told you, and this is given as 0 to 1 electron volt. What do? We integrate from 0 to 1 electron volt, right? So we put this integral here and we integrate from 0 to 1 electron volt. We go all the way down, we feed all the values. We know pi, we know value of m, we know value of h. It says that this is free electron, so we feed value of the mass of the free electron, we feed the value of h here, and as a function of that we get this is 10 to the power 21, 4.5 into 10 to the power 21 states per centimeter cube in the energy range, which is 0 to 1 electron volt. If it was 1 to 2 electron volt, then you would have fed in this integral 1 to 2 electron volt. If it was 2 to 3 electron volt, you had fed 2 to 3 electron volt, and so on, and you will find, and take that as an assignment, you will find that these numbers will vary. This total would be different. Even the range is 1 electron volt, whether you go from 0 to 1 or 1 to 2 or 2 to 3, this total number would come out to be different. The other question is that, let's say at T equals to 300 Kelvin, determine the probability that energy level 3 kT above the Fermi energy is occupied by an electron. So what is that? The probability is nothing but the Fermi function. The Fermi function we all know. This is EF. The Fermi function we know very well. Now what is the energy level? The energy level is 3 kT above the Fermi level. So above the Fermi level means E minus EF is equals to 3 kT. So we feed 3 kT here, 3 kT divided by kT, this becomes 1 upon 1 plus exponential of 3. So we solve this. So the probability for this energy, which is above 3 kT then of the Fermi level, the probability comes out, the Fermi function comes out to be 0.0474, and therefore the percentage will be 4.74%. 4.74% of the electrons or the states are occupied at an energy level which is 3 kT above the Fermi level. Okay, the next problem is that you have to assume that the Fermi level for a particular material is 6.25 electron volt, and that the electrons in this material follow the Fermi-Dirac distribution. So we are actually going to use Fermi-Dirac distribution function. Calculate the temperature at which there will be 1% probability that a state 0.3 electron volt below the Fermi energy level will not contain electron. So here 0.3 electron volt below the Fermi level, so E minus EF is equals to minus 0.3 electron volt, and 1% probability that a state is not containing electron, which means we are saying 1 minus F E is equals to 1%, convert percent into numbers, so 0.01. Now rest should be straightforward. So 1 minus 1F, we change that. As I said, E minus EF equals to minus 0.03 electron volt. So E minus EF is minus 0.03 electron volt. You feed that number here and you have to calculate the temperature. So you have to calculate the temperature. The temperature is something that we don't know, but we basically equate all of this and we get the temperature equals to 756 Kelvin. Okay, let's see the next problem. Calculate the energy in terms of kT and EF at which the difference between the Boltzmann approximation and the Fermi-Dirac function is 5% of the Fermi function. So it says that the Boltzmann distribution, the difference between the Fermi function and the Boltzmann distribution, this difference is 5%. We have to find that particular energy level in terms of kT and EF. We don't know the EF, but we have to calculate in terms of kT and EF. So we are saying that this ratio, the difference, first the difference, so this is the Boltzmann distribution, this is the Fermi distribution. It says 5%, which means we have to normalize with the Fermi function, is equals to 5%, which is 0.05 in terms of number. You simplify this and you, after simplifying, you calculate E minus EF. This will turn out to be close to 3 kT. So at 3 kT value, the difference between Boltzmann and the Fermi-Dirac distribution will be close to 5%. Okay, so let's stop here. Thank you very much, and keep in mind that it's important to remember the assumptions as we go forward. We have started with a rather complex Fermi or rather complex probability distribution function which explains the state or the probability through which the states are going to be occupied or emptied. But moving forward, we are going to use the Boltzmann distribution function to simplify the maths, to simplify the derivations. But when you have used the Boltzmann distribution function, you also know that how much percentage error will come as a function of E minus EF or as a function of difference of energy and Fermi energy. So you have to keep your assumptions always in mind, and as we move forward, we are going to take more and more assumptions in terms of simplifying the maths. So, but those assumptions will result into a percentage error. So you should also have a good feel for the percentage error being introduced because of the assumptions that we will be taking throughout the derivations. Thank you very much.